Okay, good. So let's have the third lecture by Dr. Masazumi Honda. And this is going to be the kind of most, last lecture. So it will be advanced topic, but we are very happy to have the third lecture by Masazumi. So Masazumi, would you start, please?
Okay, okay. Thank you very much for introduction. So since we have a blanco for a week, so let me start with reminding the last two lectures, perhaps for about 5 minutes. So I have an impression that okay. So focus of this lecture is on application of quantum computation to quantum field theory. And there is a important specific motivation in this context, which is a liberation from sign problem in Monte Carlo simulation. And in Monte Carlo simulation, when action is complex, we have a real time, and we have a problem in computing this integral numerically. And this physically happens when we have a topological term, real-time chemical potential, and so on. And in Hamilton formalism, we don't have this problem from the beginning. And but we have to play with huge vector space. And then I introduced some basic concepts of quantum computation, and qubit is quantum version of bit. And there are some important gates, and the rule of the game is to do something interesting by a combination of acting unitary operator and measurement. And in particular, it is known that if we have a ht and controlled x, we can approximate any unitary operators. And the real device has a noise. And there is also a tool called the simulator, which simulates quantum computer by classical computer. And the simulator does not have errors, ideally. And errors practically. And the same code can be run in quantum computer with speed up. And here are some important sets of gates, and which are exponential Pauli matrices, Hadamard gate, and control X, and so on. And then I introduced some demonstration using IBM quantum experience. And we experienced that the real quantum in computation by real quantum device, we have both statistical error and quantum error. And after that, I discussed how to implement quantum simulation of a simple spin system, which is a transversalizing model. And we constructed time evolution operator. And then we can compute the survival probability of some vacuum in free limit by full time evolution. And there is also way to compute way to find the vacuum of an interacting system. And there are many algorithms to do that. But here I explained the adiabatic state preparation vacuum. And in this algorithm, we first start with the initial Hamiltonian, which go to target Hamiltonian at final time. Then adiabatic theorem claims that if the system with Hamiltonian HAT has a unique gap to vacuum, then desired ground state is given by this time evolution. And I will apply this algorithm to Schrödinger model today. And then once we obtain the vacuum, we can compute the magnetization, expectation value of magnetization by combining probabilities having each basis in vacuum. And this is a comparison between exact diagonalization and adiabatic serial preparation. Then as we go to, we have seen that as we go to final time, we get correct answer. And this is a result for other volume. And I also computed how to compute, I also explained how to compute linear entropy by quantum simulation. And then we can compute it by using swap. We can compute linear entropy by considering expectation value of swap under the state and the consideration. And I also interested Hadamard test, which computes expectation value of a unitary operator. And then I started to explain a bit on how to rewrite quantum field theory in terms of qubits. And since the quantum Hilbert space of quantum field theory is typically infinite dimensional, we have to make it finite dimensional by some regularization. And for fermion, it's somehow easy. So because thanks to Pauli exclusion principle, and for fermion, just by putting on the theory on spatial lattice, Hilbert space becomes finite dimensional. And for scalar, it's infinite dimensional. For gauge field, when it's not topological, when we have a propagating degrees of freedom, we have an infinite dimensional Hilbert space at each side. So we need additional regularization for boson. Then I explained how to rewrite free Dirac fermion in terms of qubits. And by putting the theory on lattice, we have this lattice Hamiltonian. And then given the Fermi operator, we have a nice product of spin operator, which satisfies the canonical anti-computation relation. Then we can rewrite the system in terms of spin system, which we can simulate, we can directly analyze by using quantum algorithm. And this was the end of first day. And before going to the content of second day, perhaps it would be useful if I show you the simulation code of computing this one. So here I'm computing magnetization of Ising model by using adiabatic state preparation. And this is the Python code computing the magnetization. So do you see Python code now?
Yes, we can see.
Okay.
Thank you.
So you may be surprised that the simulation code is quite short. So for length is like this. And here I'm importing some library called QuizKit, which can be used for both simulator and real quantum device. And here I'm simply defining some parameters like volume, number of measurement, parameters, and some steps, time steps. And here I'm defining defining qubits. So this means we will use n qubits. And here I'm preparing a vacuum of initial Hamiltonian, which is the vacuum of free limit. Here I'm calling a simulator. And if we replace this line by some code using asking real quantum device, we can submit this job to real quantum device. So essential difference is only here between simulator and real device. Then by using some for loop, I'm putting time evolution operator of adiabatic state preparation. And finally, I'm measuring the approximate vacuum. Then we can get set of time, adiabatic time, and a set of magnetization, list of magnetization. So this is the atmosphere of a bit more serious code of quantum computation. And do you have any question on first day? Contents of first lectures in first day? Okay. So if not, before going to the content of second day, I'd like to explain a bit more detail on universality thing. So last week I explained that the HT and CX are universal, and proof of and this is based on the fact that any single qubit gets can be approximated by a combination of H and T. And the proof of this was given by this argument. And the important thing was by considering combination of TH-TH, we can construct, we can approximate rotation around some axis with arbitrary angle by considering combination of this one. And the important thing was that here theta is 2 pi times irrational. And there was some question on how special T is. And indeed, just for having universal sets, T is not so special. So indeed, even if we replace T by some other gate, we can compute. We can approximate any continuous gate, unless phi is very special. And if we consider, so suppose we replace T by T prime, given by this one, then T prime H gives some rotation around the axis N, and angle is given by this one. So as long as theta is 2 pi times irrational, so we can approximate any single qubit gate by combining H and T prime as well. And I also remember that there was some question on how, so what are the advantage of using this kind of discrete approximation? So first, to get the approximation with some precision epsilon, we need to use order 1 over epsilon discrete gates. But on the other hand, if we can use continuous, we can use a continuous gate directly, we need only one gate. So it looks it's inconvenient. But this kind of thing is useful for quantum error correction. It is known. For example, if we want to use infinitely many continuous gates, we have to consider algorithms to correct errors for infinitely many gates. But if we have only finite number of gates, we can consider algorithm for finite number of gates. So roughly speaking, if we use discrete gates, we have only finite number of gates to approximate any unitary operators. Then in the context of quantum error question, it's much more convenient to consider discrete gates. And now I'm going to explain the content of today. So do you have a question so far? Okay. Okay, so let us consider Schwinger model now. So we will consider Schwinger model with topological term, and this is a Lagrangian, and we have a theta angle importantly, and we could directly consider this system, but here we consider another equivalent system, which is obtained by chiral anomaly relation or transformation of fermion measure. So it is known that we can absorb theta by considering chiral rotation. So this gives the same physics. And by taking a temporal gauge, we can get Hamiltonian is given by this Hamiltonian. And pi is the conjugate momentum of A1. And the physical states are constrained by Gauss law. So this is a definite continuum description of the Schwinger model. And this model has a sign problem, severe sign problem. First, if we consider Minkowski space with real time, then vacuum expectation value is Boltzmann factor is given by exponential is, and this is highly oscillating. So we have a serious sign problem. And in Euclidean space, we have an exponential minus s, but the action is complex. So when theta is not small, the integrand is highly oscillating as well. So we have a sign problem for non-small theta. So therefore, when theta is not small, standard Monte Carlo method is not so efficient. And but this model has a accessible region by analytical computation. First one is massive limit. So when fermion is massive, we can integrate fermion out, and the theory becomes a efficient Pia-Maxwell theory with theta. And Pia-Maxwell theory in 1+1 dimension is solvable. Well, this is a free theory, for example, without theta. So we have some information in massive limit. And another important thing, particular for 1+1D, is that we have a duality or bosonization. And it is expected or believed that the Schwinger model is dual to this theory. And important thing is mass is here, fermion mass is here, and the coupling is here and here. And this theory is exactly solvable for m equals 0, since this becomes a free theory when m equals 0. So this is solvable for massless case. Schwinger model is solvable for massless case in this case. And also small mass regime can be approximated by weak coupling analysis of this bosonized theory. So in summary, we have a map of accessibility and difficulty in the Schwinger model. So when theta is small, we can approach by Monte Carlo simulation. And the massless point is solvable by bosonization. And we can use the mass perturbation when mass is small. And when mass is very, very large, we can use pure Maxwell theory. But there is a intermediate region which cannot be accessed by both Monte Carlo and bosonization approach. So here we can make prediction really here. Okay. So now let's go to numerical simulation. So we put the theory on lattice, and among many types of lattice fermions, we use stacked fermion. In stacked fermion formalism, we put the upper component on odd side and down component on even side. And the gauge field is living on link. And in Hamilton formalism, we have a real link variable and conjugate momenta. And graphically saying, we have a fermion on side and we have a gauge degrees of freedom on link. And this is a lattice Hamiltonian in stacked fermion formalism. And the theta dependence is here. We have this originally comes from mass term. And we also have a kinetic, this is a kinetic term of gauge field. And W is the inverse of lattice spacing, and J is half times G square A. And we have a commutation relation both for fermion and gauge field. And this is the lattice version of Gauss law, and physical states must satisfy this condition. And first, we can eliminate gauge degrees freedom since we are in 1+1 dimension. So let us take up boundary condition and solve Gauss law by using this one. And then conjugate momentum of gauge field can be rewritten in terms of fermions. And we have a still link variable, but the link variable can be also absorbed by redefining fermion like this. Then lattice Hamiltonian is given by this. So it looks a bit complicated, but focusing only on operator, we have only chi. This means that we have a purely fermionic system, and this acts on finite dimensional Hilbert space. So in this sense, regularization of Hilbert space is already done. But additionally, let's go to spin system by using Jordan-Wigner transformation. And using this Jordan-Wigner transformation, although it looks complicated, but we can rewrite the system in terms of purely spin system. So Z is sigma 3 on site K. Zk is sigma 3 on site K. X is sigma 1 on Xn is sigma 1 on site N. And it looks complicated, but we have only spin operators. So this is the qubit description of the Schwinger model. So now we can directly apply the quantum algorithm to this model. Okay. So do you have a question so far?
One question. So would you remind me of what J was?
Sorry, J is this one. Basically, gauge coupling. Gauge coupling times lattice spacing. Yes, yes.
So here you substituted the Gauss law there. So it becomes a 4 fermion coupling. I see.
Yeah, yes, yes. 4 and 2, yeah.
I see. And the resultant Hamiltonian in qubit system is local?
This is not local because of Gauss law. Yeah. So at this stage, yeah, I think it's easy to see in this representation. So this was originally gauge kinetic term. And except the last term, we have a local Hamiltonian. But because of the Gauss law, we have a non-local interaction.
I see. And one more question is that you chose this open boundary condition, but if I put the periodic boundary condition, then that would cause some problem of flux conservation or something.
Okay, it's not a problem, but we cannot completely eliminate gauge degrees of freedom for periodic boundary condition. So here we are solving this Gauss law, but only gauge degree freedom at one point cannot be completely fixed.
I see.
So yeah, and we can not eliminate the link variable as well completely. So we have a one physical degrees of freedom for periodic boundary condition coming from gauge field.
I see. Then you need a regularization for that.
So we need additional regularization. Yeah. Yeah. And there are some other papers to consider periodic boundary condition, but in our paper we are trying to avoid the additional regularization. Yeah.
I see.
Other question? Okay. Okay, then first let us construct time evolution operator of the Schwinger model. And again, we use Suzuki-Trotter decomposition by using some large positive integer m. Then we can divide each interaction. And each interaction looks complicated, but we can indeed express each interaction in terms of elementary gates. And the first one is trivial. We can just use a definition of RZ. And the second one, Z-Z interaction, appeared in Ising model. So we know how to do it. And the third one is XX interaction. And we can prove that this can be written in this way. And the fourth one is some rotation of XX interaction. So let us prove this quantity, this equality. And again, we can simply explicitly compute this one. So let us consider operation to 0 psi and 1 psi. And by explicitly computing this one, so we can show that CX RX CX is the same as XX interaction. So this is a proof. So now we have explicit representation of each interaction by some elementary operation of quantum gates.
Question here.
Yes.
In fact, how did you find this nice expression?
Well, okay. This okay. First, this is not invented by me. Yeah. But I think once we know this Ising model case, so we can find we can find it in similar way.
So
Yeah.
in your proof, in fact, you divide this Hilbert space. So it acts on 2 qubits, and then you divide the case for the first qubit being 0 or 1.
Yeah.
You explicitly
Yeah.
do the computation. Is that the only trick you can? So suppose I have some other Hamiltonian which may be a little bit more complicated. Then do you think this actually works for those cases?
For example,
Like
if we have a 3-point interaction,
yeah.
it could be more complicated. It would be more complicated. So this could involve 3 qubit operations,
Right.
like control X or something like that. Yeah. And another solution for this one is to rotate this interaction along along some axis, and then like this, then we can get another solution to realize this one. But this needs more gates, and this solution has perhaps this is optimal realization of this interaction. Yeah.
So those kind of try and error and with the use of these invented relations are the ways to, I see.
Yeah. But I guess I also remember that in textbook of quantum computation, there is a more systematic way to write a more complicated one, but I'm not familiar with that. Yeah.
Okay, thank you very much.
Yeah, thank you. Other question? Okay. And this is a quantum circuit for time evolution beta for NICO 4-site system. And there is also improvement of Suzuki-Trotter decomposition. So far I have considered reading order decomposition, and using Campbell-Hausdorff formula, we can prove this one, but we can improve this order by considering a bit more complicated combination. Then we have order delta t square, delta t cube. And this kind of improvement increases the number of gates at each time steps, but we can take a larger delta t in this kind of improvement. So totally we can save the number of gates by considering this improvement. And once we construct time evolution beta, we can study survival probability of the free vacuum or massive vacuum. And let us consider ground state in the large mass limit. This is given by 0101. And this problem was studied in this paper. And amazingly, this paper was published in Nature. So until I started this topic, I did not imagine that my research, my paper might be published in Nature, but this paper is published in Nature. And so let us consider the survival probability. So we have a survival probability of free vacuum, massive vacuum, and full-time evolution. So this is similar to study Schwinger effect in this system. And since 0101 can be obtained by can be obtained by multiplying x on even side. So we can rewrite this quantity in this way. So we can compute the survival probability of massive vacuum. And this is a result of simulator. And I'm plotting the survival probability against time as a function of time. So as in Ising model, we have decreasing behavior and restoring behavior because of finite volume effect. And next, I'd like to compute vacuum expectation value of mass operator. So this is a more physical problem. So we can consider chiral condensation. So we are interested in vacuum expectation value of the mass operator, psi by psi. And this is local operator, but by translational invariance, this is constant. Final answer should be constant. So instead of local operator, so we analyze the average over the space. And in spin variable representation, psi by psi can be written as a Zn. And computation of this one is quite parallel to computing magnetization in Ising model. So once we get to the vacuum, we can compute the chiral condensation by considering a combination of probability having each basis in the vacuum. So now problem is reduced to compute this one. And again, we use adiabatic state preparation. So this is the ideal time evolution, and we approximate this time evolution by the product. So ut is the exponential minus IH delta t. And here we choose the initial Hamiltonian as HZZ plus HZ. And we start with theta equals 0. And this basically, and the vacuum of this Hamiltonian is basically the same as the vacuum of massive limit. And then we gradually turn on lattice spacing, theta, and mass, like this. And at the initial time, we don't have a lattice spacing, or we have an infinitely long lattice spacing. And we don't have a theta, and we have some different mass M0. And M0 is a kind of free parameter. So M0 can be any positive number in principle, but practically it is chosen to have a small errors in numerical simulation. And finally, we have at the small t called capital T, we have a full lattice spacing, full theta, and full mass. Okay. And first, let us consider the massless case. And for massless case, theta can be absorbed by chiral rotation. So we can set theta equals 0 without a loss of generality, meaning that we don't have a sign problem in Monte Carlo simulation. But nevertheless, it is known that it is difficult in conventional Monte Carlo approach to study massless case because computation of fermion determinant becomes very heavy. But this regime, massless case, can be accessed by Bostonization approach, and we have exact analytical result. This is given by about minus 0.16 times gauge coupling. So this case should give some nice test ground of approach. So question is, can we reproduce this number by our simulation? And before going to actual simulation result, I have to explain how to estimate systematic error. So here we have an approximation vacuum by our algorithm. Let us denote it by vacuum A. Then we approximate BEV by using expectation value of operator under our approximated vacuum. And now let us introduce the quantity to get the systematic error, this quantity. And if vacuum A is sufficiently close to vacuum, then this quantity should be almost independent of T because vacuum is a eigenvalue of this operator. But practically, vacuum A is not exactly vacuum. So we have a dependence on T. So this quantity seems to describe intrinsic ambiguity of our prediction by approximating vacuum. So this quantity looks useful to estimate systematic error. And this is some test of systematic error. And in left-hand side, I'm computing time dependence of psi bar psi in this sense. As a time of T. And T is the time after we prepare the vacuum. And the red horizontal line is the result of exact diagonal organization. And the capital T is a final time of adiabatics preparation. So we see that so we have we see some oscillation around the correct value, but as we increase final time capital T, we have a smaller oscillation. So here we regard the central value as a center of here, and we regard the systematic error as amplitude. And similar behavior can be seen in improving total error. Okay, this is one thing. And another thing, another subtlety is that we have to take infinite volume limit and continuum limit. And this is the plot of the procedures. So in left figure, I'm showing a procedure of infinite volume limit. And the horizontal axis is basically inverse of physical volume. And we have some data. And but by considering fitting, we have a nice fitting at the infinite volume limit. And on right-hand side, I'm plotting infinite volume limit as a function of lattice spacing. Then we can do fitting again, and then this intercept can be considered as a prediction to continuum limit of the field theory. So let us compare these values with exact result. Okay, so this is a result for massless case after continuum limit. And I'm plotting psi bar psi as a function of coupling. And red line gives the exact result. And the blue symbols are our numerical result. And we see that we have agreement with the exact result within error. And a nice thing is that the maximal number of qubits used in our simulation is only 16. It seems encouraging. So now I'm going to massive case. And do you have a question on massless case?
May I have one question
Yes.
here? So why you could get this result only with the 16 gates? I thought that the delta
mhm.
t is very small, so you
Ah,
need to multiply many gates, but why 16 is enough?
okay. Okay. This is because of purpose. This is because so we succeeded to do fitting in infinite volume limit. So this is basically the fitting as a function of number of qubit, number of, or volume, and
Nice.
this point is the result obtained by 16 qubits, and the value at here looks a bit different from correct value, but the reason of success was perhaps 16 qubit is in the range such that we can do fitting by quadratic function of inverse of volume.
So since you have an open boundary condition, so there should be some edge modes, which are artifacts of the regularization, right?
Yes. So here I want to remove a contribution of H mode by using
So the discrepancy would be
fitting to extrapolation to infinite volume limit. Yeah.
I see. And also, our question is about so how many gates did you need?
Finally, I needed order 10,000 gates.
10,000. Oh,
Yeah.
wow.
So this sounds too much. Yeah, if we want to use a real quantum device.
So all of these results are from classical simulators?
Yes.
So if you do that on a real device, then what do you expect?
Without error correction, I get crazy answer, just crazy answer.
Nice.
Yeah. So we need to include the quantum error correction.
Nice. So
but I have not done it. Yeah.
It's simply because of the
Error.
fact that you have too many gates to operate.
Yeah.
Nice. Thank you very much.
Thank you. Other question? Okay, so let's go to massive case. We don't have an exact result, but we have a result of mass perturbation theory up to order m square. But there is a subtlety in comparison, which is that this quantity is UV divergent as logarithmic divergent of cutoff. So we use some regularization. And here, according to regularization in this paper, we subtract free theory result before taking continuum limit. And this is the result of a massive case at G equal 1. And I'm plotting psi by psi as a function of mass. And blue ones are the result for theta equals 0. And the green ones are result for theta equals 3 pi over 5. And the straight lines show the result of mass perturbation theory. So first, let us look at theta equals 0 case. Here we see that when mass is small, we have a agreement with mass perturbation theory, but as we increase mass, we have a deviation. So this can be interpreted as a violation of mass perturbation theory. And similarly, for theta equals 3 pi over 5 case, we again have an agreement with mass perturbation, and then we have a deviation at large mass regime. And since this result of this region cannot be approached by Monte Carlo simulation and analytical approach. So this value can be considered as a prediction. And this is theta dependence at mass m equal 0.1 and g equal 1. And I'm plotting psi by psi as a function of theta over 2 pi. And the red line is the result of mass perturbation theory. And we basically have agreement with the mass perturbation theory. And we have a small deviation around theta equal pi, but this may be related to the fact that the energy gap is very small, smaller around theta equal pi. Okay, so let me summarize my lecture. So most important message would be this topic is very fun and there are many things to do even now. And quantum computation is suitable for Hamiltonian formalism, which is free from infamous sign problem in Monte Carlo simulation. Instead, we have to deal with huge vector space, huge Hilbert space. But quantum computers in future may do this job. And we haven't established how to put many quantum field theory efficiently on quantum computers yet. And also quantum error correction is very important in implementing quantum algorithm in real quantum device. And here is a list of what I didn't cover. First, I didn't cover quantum error correction. And I did not explain how to put bosonic quantum field theory on quantum computer. And there are other ways to prepare a vacuum, like a variational method, but I skipped it. And there are also hybrid algorithms between classical and quantum algorithm. And there are also some algorithms to consider finite temperature and real time. And now I'm studying problem of confinement screening thing in Schwinger model with these guys. And I'm also searching critical point of the Schwinger model at theta equal pi with the same collaborator. And I'm also writing a paper on implementing quantum simulation in matrix quantum field theory and some supersymmetric quantum field theories in this guide. So this is the end of my lecture. So thank you very much for invitation. Thank you.
Thank you very much, Honda-san, for a very nice introductory lecture. So the session is open for questions. So if you have any question, please. So let me start with my question here.
Yes.
So in the last part, so here, would you, in the work in progress, you mentioned some field theories. And so in the lecture, you talked about the Schwinger model with U1 gauge theory, but U1 is in fact kind of constraint. If you go some other cases, then gauge field may be dynamical. Do you think you can treat those situations on quantum computers?
Yeah. There are other groups studying, for example, 2+1 dimensional Yam's theory. And for this case, since we have a dynamical gauge field, so we need additional regularization.
I see. So the method is quite similar to what you explained to us?
Well, So the difference is that even if we apply this procedure, we have some remaining bosonic degrees of freedom. So we need some additional regularization. And most naive approach is to impose just truncation in Hilbert space. For example, for eigenvalue of flux, for example. Yeah, and but in principle, this breaks gauge invariance, this procedure. But one may hope that since we have a cutoff only for the state with big flux, so this may not be important for studying low energy physics. Yeah, but this could be dangerous. But there are some groups using this approach.
Nice.
Yeah. And another approach is to consider to replace gauge group with a discrete group. Yeah, for example, we can replace U1 by Zn and take N to be large finally.
Sure.
Yeah, in this approach, we have a gauge invariance, but we are not sure if this procedure of limit really works. Yeah, there are some proposals.
I see.
Yeah.
So the motivation for those gauge theories would be the same, like sign program.
Basically sign problem and real time thing. Yeah.
I see.
Yeah.
So real time correlators or real time.
Yeah, real time correlator and some dynamical property of a system. Yeah. So
Nice.
yeah, I think some people. Okay, I think goal of some people are to consider dynamical hadronization in QCD or something like that.
So it's really real
related to QGPOs. Yeah.
Oh,
or collider physics or something like that.
Oh, that's great. Nice.
Yeah, this is the final goal, but practically, first we should start with lower dimensional physics.
So for those argumentation, the classical simulator is enough, or is it really necessary to use a quantum computer device?
For 2+1 dimensional case, simulator might be enough for some simple theory, but perhaps for 4-dimensional physics, finally we need real quantum device with quantum error correction. Yeah.
Why is that? So you need many qubits.
Yeah.
Nice. Nice. Thank you.
Yeah.
So is there other question?
I have a question.
Please.
Is there any attempt to simulate supersymmetric system or conformal field theory system using quantum computer?
For supersymmetric theory, I haven't seen actual implementation of quantum algorithm, and now I'm writing a paper on proposal to simulate the supersymmetric quantum field theory with these guys. Yeah, but I haven't seen concrete papers yet. And for conformal field theory, I think there are some papers. Yeah, for example, condensed matter people are more familiar with this stuff, and there are many papers on Ising model, transverse Ising model, which have a fixed critical point. Yeah.
Thank you.
Yeah. And there is also paper by another direction. So there is a paper on implementing conformal bootstrap by using quantum algorithm, idea of quantum algorithm. Yeah,
Mhm.
by Nimbao and Junyu Liu. Yeah,
Thank you.
yeah.
Okay, it's about time, but do you have a short question? Okay, so if not, so I'd like to thank Masazumi for a very nice lecture. Thank you very much.
Thank you very much.
Thank you. So Masazumi, do you plan to put your slides on our workshop homepage?
Yes. So I have already